Hello guys, welcome to our channel. Today topic is calculations of C.F.S.E. C.F.S.E means crystal field stabilization energy. Crystal field stabilization energy is very important topic in inorganic chemistry. Many questions arise from this topic in every exam, such as SLST, NEET, JEE Mains, NET, GATE, etc. The importance of C.F.S.E is very important for all type of examination. Let's start the video. Here we can see that the splitting of d orbital. Splitting of d orbital. The d orbital has 5 subcells. We know that, and it's called dxy, dyz, dxz, dz square, and dx square y square. Both the subcells are look like different structure. Here the structure will be provided. Please note down this thing. Dx square look like this, dxz, dyz, dz square, dx square minus y square. In case of dxy, dxz and dyz, 4 lobes concentrated in between the axis, but in case of dz square, 2 lobes along with z axis, and in case of x square and y square orbital, 2 lobes along with x square and y square, not in between xy and yz, along with x square and y square. These 3, dxz, dyz and dxy, is called T2g orbital, and dx square, y square and dz square are called EG orbital. Now, the case of octahedral complex, the calculations of C.F.S.E of octahedral complex, the 2 orbitals here, and one is T2g and one is EG orbital. T2g orbital contains 3 subcells, dxy, dyz and dxy. EG orbital contain dx square and dz square. Why the EG orbital is higher energy for octahedral complex? Because the EG orbitals dz square and dx square y square are higher energy due to face-to-face contact with the 6 ligand, and due to face-to-face contact with 6 ligand, it are in higher energy, but it is orbital in lower energy. Here the difference between T2g and EG orbitals is called C.F.S.E, the crystal field stabilization energy of octahedral, and in this case EG orbital is destabilized by 0.6 delta octahedral or 6 d cube. Again T2g orbital are stabilized by 0.4 minus 0.4 delta octahedral, and the stabilization energy delta octahedral is equal to 10 d cube. Okay, here note down, EG orbitals are destabilized by 0.6 del, T2g orbital are destabilized by minus 0.4 del. For high spin complex, pairing energy greater than delta, or for low spin complex, pairing energy less than C.F.S.E or del. Okay, now calculation a C.F.S.E of D for high spin. In case of D for high spin complex, there are 4 electrons in D orbitals. Since it is high spin, then the electron occupied firstly in T2G orbital, because T2G in lower energy orbital 1, 2, 3, and the last one is occupied is EG orbital. We know that EG orbital is unstabilized by 0.6, or we know that T2G orbital is stabilized by -0.4 delta. So C.F.S.E is, here is 3 electrons, so 3 into -0.4. Here is EG orbital contain 1 electron, so 1 into 0.6 minus 0.2 plus 0.6 is equal to 0.6 del. So C.F.S.E is 0.6, here minus 0.6. In case of calculus of magnetic moment, here unpaired electron is 4, number of unpaired electron is equal to 4, so 4 into 4 plus 2 is 4.69. In case of high spin, if we calculation that in case of low spin, D2 orbital is electron are filled 1, 2, 3, 4. Due to low spin, EG orbital contain no electron, so minus 0.4 plus 0.6, so C.F.S.E is equal to 4 into 0.4 is equal to minus 0.6 del. Since one pair is here, so C.F.S.E is equal to minus 1.6 del plus 1 pair. Since one pairing is here, so plus 1 pair. Okay. Now in case of Mn, H2O plus 2, chromium H2 plus 2. Here Mn is D7 state, D5 state, D5 state, and chromium are in D4 state. Since H2O is a weak field again, so both shows high spin complex. For high spin complex D5, for high spin complex high spin complex 1, 2, 3, 4, 5 is easy is T2G. T2G orbital contain minus 0.4 del, and EG orbital is unstabilized by 0.6 del. C.F.S.E is equal to 3 electron contain T2G orbital 1, 2, 3, 3 into minus 0.4 plus 2 into 0.6, here 1.20 minus plus 1.20 delta is equal to 0 delta. C.F.S.E is equal to 0. In case of plus 4 chromium, T2G EG, since 4 electron in high spin due to weak field again 1, 2, 3, 4. We already calculated same type of, here see 4 electron high spin to 4, and calculation of C.F.S.E is 0.6. So here C.F.S.E is equal to 0.6 del 0. Since there is 0 C.F.S.E and here is 0.6 del 0, so C.F.S.E of complex 2 and 1, 2 greater than 1. Now the important characteristics of C.F.S.E. If C.F.S.E increases stability, increases water exchange. Is stability increases, water exchange decreases. C.F.C increases T2G electron increases, and magnetic moment decreases. For strong field ligand increases, C.F.S.E increases. There are 1, 2, 3 categories. That is very important. C.F.C increases, stability increases, water exchange decreases. C.F.C increases, T2G electron increases, magnetic moment decreases, strong field electron increases, C.F.C increases. Excellent. That's all for today class, and the next class will be provided shortly. The topic of the next class is also C.F.C related and tetrahedral complex, for tetrahedral complexes, and some important question also.